Earlier in this lesson, we reviewed the example for the area of a trapezoid. I made the suggestion to you earlier in this lesson that you shouldn't distribute in this situation. If we're trying to solve for h and we were to distribute, we would end up with 1/2 of h b1 plus 1/2 of h b2. That would actually set us back a step, because if we're trying to solve for a variable, we certainly don't want there to be two occurrences of that variable in the equation. Unfortunately, there are cases where we don't have the option to limit ourselves to one variable. The second occurrence of the variable is already in the equation. So what are we supposed to do in situations like that? In situations where we have two occurrences of the variable that we are trying to solve for, we should do everything in our power to get both of those occurrences onto the same side of the equation. If we get them onto the same side of the equation, we can use one of our previously learned skills, remember pulling back things from earlier courses, to set us up with only one variable. Much like the d equals m over v example we had earlier, we're going to write y as y over 1. We're going to create a proportion, and we're going to cross multiply. Once we do that, and we're going to write the letters in alphabetical order as is tradition, we end up with this equation. You should recognize right away that the two x's that were previously on the top and bottom of one another are now on opposite sides of the equation. Here's one of the x's, and here's the other one. We need them to be on the same side. So in order to do that, I'm going to add ax over. Now, this seems kind of counterintuitive. All of these other examples that we looked at over the course of this lesson suggest otherwise, that you should just try to peel things away from the variable. But when you have two of them, it's impossible to make the decision about who you're going to peel away from what. You can't move the b because that still leaves an x on the other side with x, y, z. You can't divide away the z because that still leaves the x's on two different sides. So you have to be creative about the way that you approach this. We had x, y, z. We're going to add that ax over that was on the right, leaving us with negative b alone by itself on the right. The reason that we do this, and that we get both occurrences of the variable on the same side, is so that we can look at these two terms. Notice that those two terms have an x in common. Because they have a factor in common, that common factor can be factored out from both of the terms. And the question rewritten as something that looks like it should need the distributive property, but in reality, it's set up to be solved. Remember from earlier examples, if the thing we were trying to solve for was outside of a parentheses, there's no reason to distribute it. There's no reason to send it back in. You would just go back to where we were. We want to maintain the fact that there's only going to be one of those x's. And because that x is multiplied by that parentheses, I can finish the example simply by dividing by yz plus a. And we'll do the same thing over here, yz plus a, and that will be our final answer as those two binomials cancel. Our ability to get both occurrences of the variable onto the same side allows us to factor that common variable, remove it to the front of the parentheses, and then just divide away the parentheses in one step. Something similar will happen in this example where we are solving for y. We have a proportion again. It's not always going to happen that this happens in a proportion, but it is a convenient way to set up many of these examples, and you'll see a lot of them like this. 2x plus 2y equals 3x minus 3y. I jumped automatically to the distribution, the 2 times x plus y and the 3 times x minus y, because I knew that I was going to have to move some y's around. If I'm trying to solve for y, I know that I'm going to have to get them onto the same side, so I'm going to need to do that. So we'll move the 2 y's over to the right, over from the right to the left. So we get 2x plus 5y is equal to 3x. And then sometimes it just vanishes by itself. If you have numerical constant coefficients in front of those variables, even though there's two of them, if you move them together, they will just catch each other and become one on their own. We'll subtract the 2x from both sides, and we're left with 5y equals 1x, or 5y equals x, finishing with y equals x over 5. So this relatively complicated proportion that we started with, because of those numerical coefficients, boiled down into something significantly easier.